Jens and spectral distortions.
Yeah, great. Is the audio working, especially for the online? Great, excellent. Yeah, so I'm super happy that I could make it here in person. Yesterday my flights got canceled, but I got luckily got an early flight this morning. So I'm really happy to be speaking here in front of you. And one of the main reasons or one of the main goals of my talk is really to excite you guys about spectral distortions, and also to, in some sense, draw some picture of how we are going to have to move forward in order to actually go and get these signals. And you will see there's lots of physics that we're covering with spectral distortions, particle physics, early universe physics, but there's also all the stuff that we are also having to subtract to actually get to these signals, so foregrounds. And I think this is like the most synergistic kind of topic you could in that sense. It's really a broad topic and lots of things that we can discuss. So I really look forward to discussions as well. Okay, so of course, the cosmic microwave background, everybody immediately thinks about the CMB with these beautifully measured CMB temperature anisotropies. And we will hear more about this, what we have learned from the microwave background temperature and polarization anisotropies in this workshop, but I'm not going to really talk about this. Obviously, this has been a holy grail, really a rich source of information about the universe we live in and what it's made up of, and all this. We have a beautiful concordance model now, thanks to a lot of these measurements, and that has been decades of efforts really leading to that, right? But I'm not going to talk about this. I'm talking about the spectrum, the energy spectrum of the microwave background, which is what we normally get rid of, the monopole, really the average sky spectrum. So as a function of the basically energy of the photons. We're no longer looking at the power spectrum where we compare different temperatures and different directions, but where we compare the different directions, we're literally looking at the frequency dependence. And Kobe Firas has demonstrated that with the measurements in the 90s that the spectrum is extremely close to that of a black body. Yeah. The theoretical curve is covering the measurement uncertainty, so it's extremely close to a black body, the average sky spectrum. But there is these small departures that usually are talked about in terms of the mu and y parameter, and this is what we're after. We're asking questions, departures from this from the spectral shape. Yeah. So the standard mu and y type distortions, this is just a sketch from some of the very early papers by Rashid Sunyaev and Jakub Seldovich on the y type distortion and here the mu type distortion. So the y type distortion is something that you guys encountered probably with respect to the Sunyaev-Seldovich effect, clusters of galaxies where you have the hot gas upscattering CMB at low redshifts, and in that way, leading to a redistribution of photons, but a little bit only. They just get upscattered a tiny bit, and that is the so-called y type distortion, which is just from Comptonization. And one of the important things is this process is something that happens in clusters, for example, or at late stages. Late stages for me is at redshifts below 50,000. So we are, of course, really still in the primordial universe, if you think about this as the average scattering process. But this is a distortion that is created in the inefficient energy exchange regime, where you can only partially upscatter. When you can scatter very efficiently and transport photons across the spectrum by electron scattering, that's when you get a kinetic equilibrium, and that is a mu type distortion. This is a signal that can only be formed in the very early phases of the universe, when the plasma is hot enough and dense enough to actually have that scattering being efficient. So the mu type distortion, I will show different figures of it later, and it's here the solid black thick line where you can see here in comparison with the curve A black body. Never mind the details right now, but the mu type distortion is something that's coming from the early universe. And just to put this into context, this is something we've seen many times in cosmology. We have this picture of how things started and how they evolved, and our understanding of the early phases of the universe come from, to a large extent, from the CMB anisotropies, from the last scattering surface, when the fluctuations become visible, which were set up, of course, at the very early phases. And then there's all kind of interesting stuff happening at late times. We will hear about that a lot more: lensing, B modes from scattering, E modes, and of course the primordial B modes as well, coming from inflation. Spectral distortions, they teach us about the thermal history of the universe. So if there's energetic processes, energy injection or particle injection, then you can create a spectral distortion, and you're probing phases of the universe covering basically starting with a few months after the Big Bang until today. Right, the spectrum at very, very early phases, you will always just create a new black body at a higher temperature, shall we say, when you inject energy. But at later stages, like as I said, a couple of months after the Big Bang, corresponding to a redshift of 1 million or 2 million, that's when you get spectral distortions, which you can then learn about. And so the cool thing is, of course, that you can, with these spectral distortions, you can look basically behind the last scattering surface. You actually can get information from behind the last scattering surface. In particular, that's where the mu distortion is dominant. So spectral distortions, by measuring the spectrum, you can learn something about the early phases of the universe and the thermal history. This is a new window to the early universe. And here, again, these distortion shapes, the mu-type distortion is something that, as I said, is really coming from the early phases, and the Y-type distortion is a late-type distortion. And this is the standard picture that has been talked about many times. And here you can relate the energy release, the fractional energy release into the CMB to estimate what kind of parameters, mu and Y type parameters you have. So if you have an energy release of 10 to the minus 5, you get a mu parameter of order 10 to the minus 5, right? And this picture has been refined in recent years, because we now understand that this transition between the mu and Y-type distortion is not just a step function. There's a gradual transition, and importantly, this gradual transition has extra information. This is not just a sum of mu plus Y, and then you transition between the two extremes. No, you get a nonlinear scattering correction, which can actually tell you something about time dependence of processes. So in some sense, you can learn about time dependent energy release in this transition era between the mu and Y-type distortion. So this is some of the standard aspects of the thermalization calculations, and this means that by measuring the spectrum, you can really add another time-dependent dimension to the to learning about the early universe. And I just want to highlight really quickly, not going into details, we can now do these calculations, these thermalization calculations, very accurately. The Cosmotherm, which is the code that I have been working on with my team for several years now, includes relativistic corrections to Comptonization. It does properly model the double Compton process, the Bremsstrahlung process. These are the fundamental processes which are important for the thermalization calculation. And of course, at the moment, we're still doing average, average universe calculations, but we're moving towards doing even anisotropic thermalization calculations. And I'm very happy to discuss as well Cosmotherm, if anybody is interested in having the code or talking to me about it. It's not released officially. It should have been released long ago, but we're just working on making it actually friendly for the user. But we are very close now, so I'm happy to talk about that. And I want to highlight as well, I just talked about energy release distortions, so injection, decaying particles, or heating of the medium, dissipation of acoustic modes. These are examples. But you can also inject photons. If you have a decaying particle, you can in principle inject high energy photons. If it is an excited state of some type of dark matter particle, you can in principle inject depending on what kind of transition energy you have, you can inject photons. And the recombination lines, for example, from the recombination process, they are actually photon injection distortions. And these distortions evolve in a different way. And here's just a figure illustrating this. You can get a very rich spectral distortion phenomenology depending on when and where photons have been injected and what kind of time dependence this has. So there's actually a lot more information there than just the simple mu and Y type information. Yeah, and I'm going to touch on the recombination lines at the end. So let's go back to this, figure, this beautiful measurement of the black body spectrum, and these Y parameters and mu parameters. They are very small. You see the 10 to minus 5, and that means we're talking about energy release of order 10 to minus 5, right? A few times 10 to minus 5. In fact, if you convert this, is a 6 times 10 to minus 5 at 2 sigma upper limit, yeah? So delta rho over rho was 6 times 10 to minus 5. That's a tiny amount of energy, and it basically says there's nothing there, right? There's nothing to see. So why is this so interesting? So the first reason is that there's a lot of processes both within standard lambda CDM as well as new physics processes that can actually lead to distortions. And I'm going to touch on, talk about a couple of them, but here just to highlight, of course, I mentioned already decaying particles, primordial black holes, which are evaporating or just having accretion and X-ray heating. Those kind of things can happen. You can have magnetic fields dissipating. That's these are, you know, new physics examples. But then you have also the damping of acoustic modes at small scales, which is a probe of the inflationary, basically inflaton, which I will talk about briefly, and of course things with late distortions, and then the recombination lines as well as one of the very featureful spectral distortions from the lambda CDM model. So everything in yellow is lambda CDM. I should have stressed that. In any case, this is really exciting. There's lots of distortions, and Phyras was up here. So none of these distortions should or would have been expected to be detected, right? But if we just improve by an order of magnitude, we already will be seeing distortions from the late, you know, energy release from structural formation and so on. And if we, of course, go into the regime of PIXIE and potentially instruments that are even more powerful, and I'm going to talk about some of the ideas there, then we might be even reaching to these levels of the primordial damping signals. Yeah, so this is really interesting and exciting. The other reason why this is really, of course, very important to, you know, think about in CMB anisotropies, we have moved forward in both sensitivity and angular resolution for many decades. Yeah, at least three main space missions have been flown, and we have been, you know, improving vastly the you know, resolving power and also sensitivity. Spectral distortions are still in the state of the pioneering stages. You know, really, Phyras is still the benchmark. That's 25 years ago. So we can, technologically speaking, we can actually improve those limits with, you know, there's no reason to believe that we cannot actually go several orders of magnitudes better than Phyras. And one of the ideas that has always been brought up is PIXIE, which is a Fourier transform spectrometer. So it points towards the sky with two barrels, and it basically does a Fourier transform of the sky to really get an energy spectrum with extremely strong control of systematics and absolute calibration. And this was promising 1,000 times at least improvement over Phyras. That brings you into the ballpark of interesting signals with respect to lambda CDM distortions. And I will talk about that a bit more. And then in addition, it also has polarization capabilities, the concept, and it would have actually been able to you know, go into the regime of 10 to minus 3, a few times 10 to minus 3 on the 10 to the scalar ratio. So this is a concept that has now been, you know, updated, upgraded, multiplied, and so on. That's the kind of strawman concept that we're still thinking about. And I want to highlight that one of the big problems is to get to the spectral distortions, we need some stronger low frequency coverage. And that's one of the big challenges which probably we'll have to tackle as a real step towards a realistic mission. So I just want to highlight that immediately. But PIXIE, although, you know, so far it hasn't been, you know, funded, it was proposed twice already, and we were actually gearing up to propose it again this just basically next week. But unfortunately, the cost estimates were coming out a little short in terms of the funding, the budgetary constraints. So we couldn't go forward with that, which is a big pity. But nevertheless, there's activity. There's Cosmo at Dome C, which is the Italian colleagues trying to do something from, you know, the Concordia station at Dome C, doing a ground-based measurement. This is not just fantasy. This is really actually people already starting to, you know, build a cryostat and set up the system and so on. So this is something that could be potentially reaching a factor of 10 or so better in terms of sensitivity than Phyras from the ground. Of course, from the ground you have the atmosphere, which is really challenging to take care of. But nevertheless, there's really some hope to go forward even from the ground. But you wouldn't go to the mu distortion. There's hardly any way to go, at least not from the expected mu distortion from damping. We also have, we're talking about Bisou as a balloon bomber experiment, which is led by our colleagues in France, Bruno Maffay and Nabila Naganim. Cosmo was Paolo De Bernardis and Silvia Masi and also Elia Battistelli, just to mention the main key people there. And this is something that we are actually now coming up with a concept. It's a phase 0 study that we're doing, and we're trying to think about, you know, how we can, what we can do. And again, in that, this would be again both helping technology development as well as, you know, probably improving spectral distortion limits by at least an order of magnitude over Firas. Balloon is much better in terms of atmosphere, but it's still very, very difficult, right? So you really ultimately want to go to space, and we had put forward these Voyage 2050 white papers, 3 main papers and another one on line intensity mapping, which you know, Jacques Labrouille in particular was coordinating across all these different science cases, and we put one specific on spectral distortions forward, and we are very happy that this was recognized by the ESA report. So setting the sails for spectral distortions is actually lending from the press release that the ESA report had, which was, you know, setting the sails for basically a space program. And spectral distortions, 3 main themes were identified, and one of them is the early universe physics and the probe of early universe physics. That is where spectral distortions were mentioned as a potential L-class mission, you know, a contender. Now this is a long time frame, and we need to really try to organize towards that, and that's one of the things that we have now been picking up. So there was a meeting in 2000. Sorry.
Can you comment on the third one, on what is new physical probes of the early universe? Which kind of probes, you know?
So it's new probes of the early universe, new physical probes of the early universe, and spectral distortions were mentioned in that category, mainly because of the power, constraining power on the small scale power spectrum. And the other probe that was mentioned there is gravitational waves, but not a la ELISA or LISA, but in slightly different frequency bands, which has a lot of challenges as well. So both of them are, I think, very futuristic, and therefore also this very long timescale investment. And yeah, one of the things is really to organize towards this, and where this is the, you know, a meeting that we had at CERN in 2018. I think several of you were actually also there, of course. And here's just a nice couple of pictures. Here's Rashid Sunyaev sitting in the audience, and very happy that we, you know, have brought together the particle physics community and the theorists in spectral distortions, also some experimentalists, of course, in spectral distortions. Subodh Patil was the main person behind this and really driving this forward. And I think this meeting was, this is really the meeting which then you know, led to the white paper in some sense, to this white paper that had you know, this being identified. So this was really, really important. And we have now just gotten last week the news that we will have another meeting which we can have in the Lawrence Center next year. It will only be in October next year. Again, Subodh was one of the key people pushing this forward, and then Emma Di Mastrogiovanni and Dan Melberg and also Jacques Labrouille. We're trying to coordinate this, and one of the really two of the really important goals is start building a community behind this science case and growing it, because at the moment is you know, there's lots of people which are active, but we need more activity, and then also bring experimentalists much more on board. And I mentioned already the low frequency coverage is one of the problems of spectral distortions, and these are, you know, some of the questions that we would be really addressing. Is there more theory development needed? What are the component separation problems that we, you know, and what methods do we need? How do we need to combine data sets? So again, this synergistic, you know, very, very synergistic perspective, and then new technology ideas for the low frequency coverage in particular, because that is one of the big challenges of FIRA. So this is hopefully going to be something that will be on a good, you know, on a good step towards a real credible proposal. Okay, and just to finish this, overview before we now go through a couple of distortion signals. This is my group in Manchester at its peak, so it has now trickled down. It's we're now 5 or 6 people in the group active, but we had a lot of activity in Manchester, in particular gearing up for the for this white papers, and all of these folks have really contributed to this, and yeah, so this was really exciting, and it was just before the pandemic struck, so we were allowed to do this picture, but then a week later we wouldn't have been allowed to do this. So it was really, but in any case, we have been working hard on many things. So let's go through a couple of distortion signals, because at the moment it's all just like mu and y distortion, and okay, there's some line spectra and so on, but let's look at concrete examples. So if we just consider the energy release coming from structural formation and late injection, in fact it's just a cumulative flux of clusters of galaxies and group size clusters. The smaller clusters in the mass range of 10 to the 13, several times 10 to the 13 solar masses, then this would be the signal you would be seeing. So this is really the intensity in Jansky per steradian as a function of observing frequency, and I'm showing this here in logarithmic units. So this is the Y-type distortion, where you have here the negative branch, the photons being moved upwards, so removed from the low frequency, and they appear at the high frequencies, and the null, the crossing null, is at this 217 gigahertz. This is the typical Y-type distortion, also known with respect to the non-relativistic case of the Sunyaev-Sedgwick effect. And this Y-type distortion would be of order, 2 times 10 to the minus 6, could be maybe 5 times 10 to minus 6, but in that ballpark. So this is really basically 1 order of magnitude below the Fires limit currently. And PIXIE, just for rough guidance, that would be the sensitivity that PIXIE could be in principle reaching. So this signal would be a huge signal, and that is the reason why you can now ask even small corrections to the signal, coming from the fact that the electrons, which are really scattering, low redshift electrons in these groups and clusters, they're actually pretty hot. They can be several keV hot, and then you get a relativistic correction to the signal, which is just basically like a little bit of additional upscattering that you would not be otherwise achieving in the early universe. So this signal is something that you would also be seeing with PIXIE at a at the level of 15-20 sigma, even with foreground marginalization. So what does this allow you to do? Well, you can actually calibrate or ask questions about feedback processes. So this is the Y parameter, expected Y parameter, and then here the temperature, the effective relativistic electron temperature, and simulations. They cover a wide range of the parameter space, depending on how you tweak the models and so on. But with PIXIE, and here as an example, Pristine, let's not go into details, would be basically homing in onto what is the real physics behind these, the heating mechanisms. So this would be allowing you to really understand feedback processes and, what is the cumulative hot gas in the universe, right? So that's quite interesting, but it's a low redshift signal. And, one might be even saying, okay, well, if you look at clusters of galaxies and in X-rays, for example, you can get a lot of them already. But it turns out that you can probably, even with futuristic things like Athena, you will only get like 80% of all the hot gas in this way. With spectral distortions, you would basically integrate the whole, average hot gas. You would have all of it. Okay, but for the primordial universe, and this is, I think, one of the main reasons why this got mentioned as well with respect to the Voyage 2050 report. We have these small, acoustic signal, the acoustic modes in the CMB. And we know that the power spectrum is really going down at small scales just from silk damping. But if you really go back into the early phases of the universe, then you would, in principle, of course, expect just from inflation a scale invariant power spectrum being set up. So there was power and fluctuations at small scales, but these damped away. And this damping process is the equivalent of heating. You can actually, by just viscous processes, you basically extract energy. The fluctuation power, the entropy in there gets converted into photon entropy, and thereby starts distorting the spectrum. And the physics behind that is super simple. If you just imagine, a box with two black bodies, one a little colder, one a little hotter, just an average spectrum, and now you shake the box, you just mix it up, you would get uniform distribution. That's Thomson scattering, by the way. So nothing changing in terms of the energy of the photons, but they would be just smeared out across the whole box. If you just take the two distributions and add them, you get the purple line. And you can see, if you compare this to the average temperature spectrum, then this is not going to be a black body anymore. It's just a simple statement of saying, if you add two black body spectra, you will not get a black body. And that starts then a thermalization process, because this is not in equilibrium with the matter and radiation. They are not in equilibrium, so they will just start thermalizing. And if you go to the very small fluctuations, that is of course then equivalent to a Y-type distortion initially, which then gets Comptonized and thermalizes. And this is actually something that was used back in the days to constrain the power spectrum and the amplitude of the small scale power spectrum, even with COBE Firas and COBE DMR. You could do, there's a paper by Wayne Hu and Joe Silk. I didn't add this slide now, but you can in principle learn about the power spectrum. So here's the prediction for the signal from just using the best fit parameters for Planck for the power spectrum, because of course, if you have small scale power being much larger, you will get a larger distortion, more fluctuations, more dissipation, more heating. If it's very small, you would get a much more small distortion. But this is, if you take the standard power spectrum parameters, this would be the predicted lambda CDM parameters. This is assuming slow roll, standard slow roll inflation. So it's a vast extrapolation, because the modes that are really dissipating we are talking about modes which are at scales of 10 to the 3, 10 to the 4 inverse megaparsecs. So just to highlight that even further, we know the power spectrum amplitude very well at large scales. So large scale CMB scales, right? The measurements of the temperature fluctuations, they have told us very well. But then at small scales, things become much more uncertain. And at these intermediate scales, here it's shown to vastly small scales, obviously. But there's a very strong limit from the existence or non-existence of primordial black holes at various masses, which gives you basically this amplitude, which would be the vision of like a horizon scale collapse of the fluctuations into a black hole, right? And that can be ruled out by certain measurements. And then there's here constraints which come from basically annihilation signals of dark matter fluctuations and mini halos. So they are quite uncertain. But if you're talking about spectral distortions, you probe these scales in addition. So the mu distortion in particular is generated here in this regime 50 inverse megaparsecs to something like 20,000 inverse megaparsecs. And if you take Firas and convert that into limits, then you get these upper limits on the power spectrum. This already rules out, for example, supermassive black holes being formed primordially. So this already says there cannot be a large dominant fraction of supermassive black holes from just horizon scale collapse, because the amplitude is of order 10 to minus 4, 10 to minus 5. So this is what spectral distortions can add to this picture. And then of course PIXIE with foreground marginalization, you can push it down to the the level of the lambda CDM signal. However, you see, if you just naively extrapolate, you cannot really see the lambda CDM distortion with a PIXIE, with the standard PIXIE setup. And we have talked about multiple copies of PIXIE and also a low frequency instrument and a high frequency instrument. All those things are attempts to fix that, to get the foreground basically handled in a better way. And this is where the real work has to happen, because PIXIE itself is only 60 centimeter big. The telescopes are very small. These are not like huge telescopes. We're not at the limit in that sense, but it seems that just copying PIXIE and making it basically a bigger light bucket is not enough. So we need to come up with creative ideas there. And I want to highlight this connection of small scale power with the primordial black holes. In addition, of course, this is something we will also hear in this workshop now about primordial black holes and how they form and gravitational waves from them, all these exciting things. if you just again convert these power spectrum limits, here CMB anisotropies, and then the extrapolation, for a standard spectral index, slow roll, just no running, no nothing, then this would be the power. PIXIE and Virus, these are the more concrete limits. And then if you now imagine that you want to create a primordial black hole of a solar mass or a few solar masses or maybe intermediate mass black holes, you would need power at this level, right? And that means somehow it has to get there. It has been shown that this rise cannot be arbitrarily steep. Within single field inflation, you get a k to the 4 maximal steepness. So that means, depending on where you want to constrain, you will have, constrainability with PIXIE itself. And I want to highlight here, this is a very primordial constraint. This comes from mu distortions from redshifts 10 to the 6, 10 to the 5. This is not mergers today, well, on cosmological, redshift related, recent mergers, where there's a lot of physics going from converting primordial black holes, which might or might not exist, into some black holes that now merge, or if they are, coming in clusters or all these things. This connection is much cleaner in some sense. The primordial connection is much cleaner probed with spectral distortions, and we are now working on basically understanding, how this mapping can actually be refined. There's been very nice papers on this topic previously, but we're trying to. This link has to be really refined. That's one of the theoretical things I believe which need to be improved. Okay, and I want to also highlight that gravitational waves can also be constrained with spectral distortions, which I think is a very neat aspect. When you look here at the figure that is, it comes from a paper by Campetti and Komatsu and co-workers, where they have compiled here the expected tensor limits, basically at the larger scales from CMB, so Lightbird type measurements, and then here pulsar timing array, interferometers, and so on. They are promising these kind of constraints, and of course there is some constraints here in these different bands already. Spectral distortions would nicely bridge this gap between these two scale regimes. Now, of course, again, you can talk about scales here, and you can, when you have now some early universe model, you can have actually bumps in the power in terms of primordial physics, and you can, in principle, by this multi-messenger approach, you can probe different models. If the models have power which is flat and just rises here, of course, spectral distortions will not be doing anything, but you can, by combining all these different data, you can actually do something. Diego has another question.
I don't think it's working. Is it working? Okay, I cannot hear. Yes, for completeness, in this band there is also Gaia bands. Sorry, Gaia constraints. I don't know.
Yeah, I don't know where they map, but yeah.
Well, those are at this ultra large scales before CMB.
Right.
And in my mind, they are close to PIXIE, so maybe complementary.
Right. Thanks for that comment. Yeah, we literally just took the work from Campetti and co-workers and basically converted and said, well, there's another one here. And of course, one should immediately highlight the limits are very comparatively, weak. Because it turns out that if you have a gravitational wave going through the fluid, it doesn't damp that much. It excites, fluctuations that then lead to B-mode polarization signals, but the dissipation is very weak. Gravitational waves go through the universe basically unimpeded, right? And that's manifested by not heating the medium much. Yeah, but there's still constrainability, and of course it's futuristic, right? But there's this regime, which is interesting. And in this way you can constrain phase conditions and all kind of new physics examples can be thought about, but it's just another aspect of the distortions. Okay, I need to have an eye on time, but I think I have that's about what I thought. There's also anisotropic distortions, which is a really interesting topic. I don't want to go into details, but you basically can think about if you have anisotropic heating mechanisms, the heating rate is modulated, you get mu distortions which can be modulated. And if you, for example, imagine horizon scale modulations at different phases, then this is a probe of non-Gaussianity. And we have, with my group and also other, this goes back to some ideas by Enrico Paja and Matthias Aldariaga, and then also Gans and Komatsu followed up on this. You can probe primordial non-Gaussianity at very, very small scales. It's a very ultra squeezed limit probe, and we had a recent paper where we actually updated the forecasts for Lightbird, showing that you could potentially at scales of a few hundred or nearly 1,000 inverse megaparsecs, the squeezed limit non-Gaussianity can be measured. In principle, there's a lot of particle physics aspects you can probe: decaying particles, excited states of dark matter, things like dark matter and standard model particle interactions through cooling processes, and also photon injection distortions. They can actually all be, help to shed light on various parameter spaces. And I think there's a lot more work that can go into this direction to actually, understand how you can really learn about early universe and particle physics in this way. And I want to just highlight here, of course, we know about the edges observation, which is like, one of the possible reasons why the signal could be so large is because maybe there is a non-standard photon background at low frequencies, and that, of course, links to the so-called arcade access. And I wanted to say a few words about this neat small paper that we had with Gil Holder just a couple of weeks ago now, but let me skip this. But I just want to stress, if there's actually small at low frequencies, so I'm talking about the radio, if there's actually distortions there, they might be, they might be primordial. There might be something coming from some particle decays or some accreting black holes, or there's physics there we can learn, and really shedding light on this is really, really important. Okay, and I want to just close with mentioning the recombination lines. This is a figure that Luke Hart, my former PhD student, has compiled, and it just shows really the redshifted signal from the recombining plasma at redshift 1000. Right, so hydrogen and helium recombine, and as the electrons go to the ground state, they emit photons at highly excited states, and that's how you get all these really, really nice features in the spectrum. This is a very small distortion. It is, in comparison, it's the smallest predicted, or one of the smallest distortions, about a factor of 6-7 below the mu distortion from lambda CDM. But because it has so many features, you can actually more easily extract it with respect to foregrounds, at least the standard foregrounds like synchrotron and Bremsstrahlung and so on. Because the features have some, that allows you to distinguish this signal. And of course, you can, we can now calculate the signal accurately and very quickly, so that you can, in principle, ask the question, what can you do and really constrain parameters with this? And there was a paper by Luke Hart and Aditya Roti where we did a forecast for, futuristic perspective on measuring these signals and what we could learn. And we are now working, for example, on how does early dark energy change the recombination lines, because you can actually probe different phases of the universe, and if there's some expansion history changes, then the positions of the lines, the shapes of the lines will change in a similar way. If there's, for example, variation of fundamental constants or things like that, you can actually change and modify the spectrum. And this is really exciting in terms of, again, physics and particle physics connection. And the elephant in the room is, of course, the foregrounds, which I don't have time right now to talk about anymore. And I just wanted to say that I'm lucky that Matthieu Remazet and also Aditya Roti really joined this whole effort of really getting machinery going to do spectral distortion, anisotropies, and spectral distortion really extraction, which is it's a different problem which we're not so familiar with. CMB anisotropies has different ways of doing things, so you have to actually modernize and or come up with new creative ideas. And there's a lot of effort which needs to go into that in the future. And this is, again, the synergistic approach where you need to come and combine different data sets. You need to actually understand how to use the information from different data sets. Can we use the galaxy catalogs to actually predict what kind of emission, net emission should be there? And I mean, if we really imagine on a timescale to 2050, we might have all that information or a lot of that information available. We need to actually understand how to make use of it as well. So there's lots of work needed there, and that's one of the bullets in the workshop item that we are planning, of course, as one of the crucial things. Okay, so I will stop here and hope that I excited you a little bit about spectral distortions, and that there's actually lots of cool physics in there, both in terms of how they form, but also what we can learn about new physics and standard physics in the early universe and particle physics. And I think there's really, we need to try to move forward and really get this measured. I'm hoping that that will be something maybe in this time frame, 2050. Okay, thank you.
Thank you very much. So I'll start with the questions from the room, maybe.
Thanks for a very nice talk. Could you say more about this paper with Gil Holder recently? I don't understand how can you explain edges with.
Yeah, I'm happy to just say 3 words about it. The arcade excess means there's at low frequencies there's a distortion or there is an excess that people have actually talked about, and it can't be explained apparently with the cumulative flux, just simply modeled with cumulative flux of radio galaxies. So there is an excess, and the question is, and this excess roughly would be looking like this. So this is the CMB part, and then this would be the excess, the radio excess, right, as measured by arcade. If this excess is really cosmological and isotropic, that means that a cluster sitting at a redshift of 1 or 0.5 will be seeing a CMB which is distorted, has this excess, and it would then upscatter this. In the normal CMB part, we know what that does. It's just the standard Sunyaev-Seldovich effect, where you just move photons from here to the higher frequencies, and you get the null. This is, of course, a very, very large Y parameter. It's not even correctly calculated. It's just, the standard distortion. But here, at low frequencies, a similar thing would be happening, and that means that you now see an excess of flux in the direction of a cluster with respect to the background, whereas then at higher frequencies, you would see a decrement. So you can have this source sink structure, which will allow you to basically test this hypothesis. Is it really cosmological?
Redshift 17, right?
Correct.
How do you
correct, but so the connection to edges is just that this excess could be something that is potentially present even at redshift 17, and therefore enhances basically the total signal, because it has a huge excess over the CMB. But we, at the moment, if we measure here, and if we just look at the spectrum, we actually don't know, is it really coming from low redshifts, right? But with this effect, you could at least test, is it something that is, distant to us? And I agree with you that redshift 17, there's no clusters there, so you cannot really, measure, of course, at redshift 17 and probe it there. But it would be very, very nice to see that it is actually consistent with at redshift 1, for example.
And you don't break up CMB observations in any other ways?
No, I mean the virus measurements were limited here basically to this part. And you can, of course, for example, if you inject photons at low frequencies, you can actually heat the medium, and in that way you get a Y distortion, which then can be constrained by a virus. But if you do this at late times, the heating process is not very efficient, and you can actually evade. You can get around the virus limit. But that is a detail that needs to be actually calculated. And in this paper with Boris Bollier, we attempted doing that, but we are now, of course, trying to do this more properly. Excuse me.
More questions?
Yeah, I just had a question about. So you said that in the case the previous case, you had some features, right, that you could look for, and that's even though the signal is much lower, because there are features you can see it much more easily. But these features are moving. I guess they depend on some parameters, right? So you don't have a template that you try to match.
Yeah, you're talking now about the recombination lines,
exactly,
right?
Yes.
This is really the redshift 1000 universe.
Yes. So you see these features, and but these features depend on some of your parameters, right?
Yeah. For example, the helium abundance, just for illustration, or of course the baryon density. If you have more baryons, that means more hydrogen. You will get, the leading order is just an up and down of the spectral template. of course, with small modifications because of expansion history, you know, all these kind of things.
Yeah.
But YP changes the mixture of the helium to the hydrogen spectrum, which is quite different. The hydrogen spectrum looks quite different than the helium spectrum. This is the helium lines, and this is, you know, the hydrogen lines, and that admixture then changes. So you can, in principle, learn about YP is actually the parameter that you can most constrain, or you have most leverage on, and that is primordial helium. That's not, you know, that's really redshift 1000 helium. And there's lots of things one can actually think about, maybe modifying this as well. And of course, the shape of these lines encode the dynamics of the recombination history, which is another thing. And we heard probably, we will talk about this during the workshop, the Hubble tension, maybe some modification to recombination. Primordial magnetic fields have been thrown into the mix, you know, could be changing, or maybe even, you know, some fundamental constants that are varying. That will change the recombination history. This will change the recombination spectrum. So you can probe it directly with looking at these lines, which are very small signals. But it's hard. But this is a way to learn.
Yeah, so you look for a template, right? That's
yeah. I mean, you can literally calculate as a function of parameters. For example, the EDE parameters. Yeah. We have the calculations. You can just calculate how does it change. Yeah.
Okay. So let's thank Jens again. And